All right, so I'll just get us warmed up here, and then we'll do this. Okay, so this is going to be a combinatorial graph one, uh, and it's also a classically important thing. But usually this one's pretty fun. It's going to have lots of pictures and less of this analytical math. We're back to thinking combinatorially. Okay, so let me introduce these basic problems. All right, so in vertex cover, you want to choose a set of vertices. Oh, we've done vertex cover before in a bipartite setting, right? So you want to choose a number of vertices so that every edge you're choosing at least one vertex, right? But intuitively, like maybe a vertex is high degree in the middle, you might want to take because it seems to cover more edges at once. That algorithm doesn't quite work. The greedy algorithm doesn't quite work, but still it's reasonable. Okay. So I think I've asked people to try to solve this in the past, but then it's too big to like have you guys describe a solution. So maybe like here will be an example of a vertex cover. So I don't know if it's the best example. Maybe you can tell me if there's any way to improve it just by looking at it. But every edge, I'm taking at least one of the endpoints. Okay, and you want to do that. Okay, so that's one of the two problems we're going to discuss. Um, right. Oh, sorry. Yeah. So what's the minimum cardinality vertex cover? Okay. All right. Or I can give you some value k and say, is there a vertex cover of size k? All right. I guess I wanted to make this point, which is maybe not surprising. There's some difference between minimal vertex covers and minimum vertex covers. Okay. So this one with 3 on the left is minimal. If I took out any vertex, it will cease to be a vertex cover. But it's not the best one because you can do 2. Okay. So, really naive algorithms won't necessarily work. You might get stuck at these minimal, but not minimum. All right. Oh, here's a more exaggerated example. Good. Okay. And then you know what a matching is, right? So a matching, you want to choose a bunch of edges so that the endpoints are disjoint. We did this before in a bipartite graph. There's 2 sides, a left and a right. Now I'm just giving you a general graph. Okay, so both of these problems we know is polynomial time and bipartite graphs. We've done them already. But here we're looking at things in general graphs. Good. So here would be an example of a matching. All right. Yeah, I give you a graph. I ask, can you find a matching of size k? That's how I would phrase it as a yes/no question. Okay. Otherwise, the problem is just to find the biggest matching. Okay. Same point as before. Maximal does not mean maximum. It's not hard to find situations where you get stuck. Okay. All right. So here's a problem I set up. Only 16 vertices, right? So sometimes I think like even these small graphs are actually really hard for us. So in this graph, what's the biggest matching you can find? How did you get 8? Yeah, okay. So I planted a very clean solution inside this. Yeah. So what I've learned from teaching is that you first draw the matching, then you draw a bunch of other edges and try to throw people off. Yeah. And then you make everything blue afterwards. Yeah. Okay, good. Um, okay. Now these problems are dual to each other, which is I think the point we also made in bipartite matching. So in matching, you want to take as many edges as possible, but you can only take one edge per vertex, right? Because they have to be vertex disjoint. And in vertex cover, you're trying to take as few vertices as possible while taking at least one from every edge. So you have the same duality just like we had with packing paths and covering paths with edges. Good. So, like any dual situation like this lemma you basically get for free. A maximum matching is at most the size of any minimum vertex cover. Let's see if there's a proof set up for us. There is. Okay, I'll go through it somewhat quickly. I think I was supposed to erase, it doesn't matter. So if you took any matching, right, like these yellow edges will be matchings, and any vertex cover, well, you know that your vertex cover has to have at least one edge, one endpoint of every edge in your matching, right? Because it has to have one endpoint of every edge, let alone the ones in your matching. So meanwhile, all the matchings, their endpoints are disjoint, right? So each edge is covered by different vertex from the vertex cover. So that means, okay, the number of edges you're matching is at most the number of vertices in the vertex cover just from looking at every edge of my matching, and one of those two endpoints have to be in the cover. And there's no repeats because they're disjoint. Okay. So again, this doesn't really even have that much to do with vertices and edges. It's just coming from the incidence, this less than equal, greater than equal kind of thing. Okay. So just another example. Good. So the real question is, are they equal? Okay. That's not obvious. Oh, okay, sorry. Okay, does anyone feel, okay, who thinks, okay, I'm going to ask, do you think they're equal or not? And if not, then I'll ask you to supply a counter up afterwards. So the first question is, who's not going to vote? Good, 3, 4, 5, okay. 4 not voting. Who thinks that they will be equal? Okay, say that's like 40%. And who thinks they will be unequal? Which means there will be a strict less than. Oh, 0%. Okay, so I don't know. Okay, last week of school, we still have lots of liars. All right. Okay. Uh, okay, that means none of you got it right. In fact, they're not going to be equal. Can anyone think of a simple graph um, uh, where actually it's not equal? So if I had like a star, a vertex and a lot of edges going out, then the vertex cover of 1 is just taking the middle one, and you can only take one edge. So actually, they'll be equal. Yeah. That's right. So like a triangle like this, you can only take one of the edges, but you have to take at least two of the corners. Okay, so even though they're primal dual, just like other problems we've seen, they're actually not equal this time, which can happen. Okay, so it's good for you to see one example where they're not always equal. Okay. All right, so good. So this is the question we're going to try to address. Okay, so you have two different problems that are dual to each other, although duality is not as strong as before. Since the values aren't exactly equal, it's possible that one's easy and one's hard. If the values were always equal, then if you can solve one, you can solve the other, right? Oh, I want to know matching. Let me find the minimum vertex cover and just output that number. Okay? So it's possible this time that they have different things. All right. So you have two questions, two choices each. For vertex cover, is it easy or hard? For matchings, is it easy or hard? I think it's the last poll of the entire semester. Okay. So who is not voting? Okay. All right. Who thinks vertex cover will have a polynomial time algorithm? Good. One. And who thinks that it's going to be NP hard? Okay. Okay. Now let's go to matchings. Who thinks that we'll get a polynomial time algorithm? Okay, and who thinks it will be NP hard? Okay, all right. And you already know in bipartite graphs we have algorithms for both. So I guess the general feeling is that for both of these problems, when we move into general graphs, it's suddenly going to become hard. Okay. Although some people thought that there was better hope for matchings than for vertex cover. That will be a great place to pause. So when we come back, we'll find out if vertex cover is NP hard, if matching is NP hard, and it'll be kind of our last algorithm slash reduction stuff for the semester. Okay. All right. Thanks, guys. All right. Last lecture, we started this last time, so let me remind us what we're doing. So vertex cover, you want to choose a minimum number of vertices to cover every edge, at least one endpoint from every edge. We've already done this in bipartite graphs. And matchings is sort of a dual problem. You want to take as many edges as possible so that they don't intersect at any endpoint. Okay, so those are two problems. They are dual to each other. Yeah, here's an example we did. You can have edges packing into the vertices or vertices covering the edges. Okay, just like packing and covering paths. Good. So, right. So unlike last time, although maximum matching is always less than equal to minimum vertex cover from duality, they're not always equal. So in this simple three-edge graph, you can only take one edge in any matching, but you need to take two corners in any vertex cover. Okay, so these values are not always equal for all problems. Good. So this is roughly where we left off. Uh, so the basic questions are, which of these are polynomial time and which of these are NP hard? Uh, since the value of the minimum vertex cover is not always equal to the value of the matching, it's actually possible to get different outcomes. Okay, so most of you voted that vertex cover would turn out to be NP hard, and most of you also voted that matchings would be NP hard, although there was a little bit more support for matchings having a polynomial time algorithm. Okay, so let's see how it plays out. All right, so vertex cover is NP hard. I was supposed to erase, okay. Okay, so we are going to show vertex hard is NP hard, vertex cover is NP hard by reduction from the independent set problem. Okay, so on the graph on the left, I've highlighted an independent set. There should be no edges connecting any of the vertices highlighted in teal. Okay, and I claim there's some kind of relationship between independent sets and vertex covers. Anyone see it? Oh, you want to look at some kind of dual graph where you exchange the rules of edges and points? Yeah. Independent set is just trying to choose a lot of vertices so that they don't touch each other. Trying to take as much as possible. Vertex cover, you're trying to take as little as possible while covering every edge. So I'm suggesting there's some kind of clean relationships between independent sets and vertex covers. Not necessarily. Okay, So on this graph on the right, I've also highlighted that same independent set. Do you notice anything about all the vertices that aren't in the independent set? So I'll highlight them. Ah, so for every independent set, the opposite set of vertices is a vertex cover, right? So independent set guarantees for any edge, you can only take one of the endpoints. So you'll always leave one endpoint out. Okay. So this is complementary. For any vertex set, you take the opposite vertices, that'll be independent. For any independent set, take the opposite vertices, you'll get a vertex cover. Okay. So maximizing the independent set by just taking the opposite vertices is the same as minimizing the vertex cover. Okay, okay, good. So uh, that one turned out to be NP hard just from flipping the vertices over. Okay, good. All right, so right. Okay, so that turned out to be hard, and now we'll focus on matchings. Okay, see how this turns out to be. All right, so some of you last time voted that it was hard, and some of you voted that it might be easy. And I was wondering if anyone wanted to give any reasoning uh, for one way or the other. So there's some kind of bound on the size of any matching. Uh, I guess of at most n or n over two. Oh, okay, okay. So maybe just because the vertex cover gives you a bound on the dual problem, but a similar argument could have been made for vertex cover. Matching gave a bound on vertex cover, a lower bound. Yeah, why is upper bound better? Well, upper bound is how low it can go. Okay, so you believe that maximization problems should in general be easier than minimization problems. You could be wrong. I don't know. But maybe, I don't know. I don't have a strong thing for or against. In my experience, not necessarily, but any other intuitions or ideas either way? All right, well, I threw a few down. I don't know if they're very interesting. Okay. Um, okay, maybe one reason why it might be hard is because the dual cover, vertex cover, we just found out is hard. And we often, at least so far, usually like one problem has similar behavior to its dual problem, right? Then not necessarily since the values aren't equal. It doesn't force it to be hard. On the easy side, we know how to do bipartite matching already. We've done that with flow. And I don't know, finding a maximal matching is easy. I don't know if that's very compelling, but I'll just try to make stuff up. Okay? All right, so who knows? All right, so, okay, so maximal versus maximum. Okay, we're going to do a little bit of a foray just to study the object. So in that example from before, many of you spotted this maximum matching. But this would be like a maximal matching. You couldn't add any more edges to this. Okay, they're not necessarily equal. Okay, so kind of similar in spirit to our spanning tree lecture. I want to just tease out this maximal versus maximum relationship. So if I have a maximal matching and a maximum, A is less than equal to B always just by definition, right? But I guess you can ask, is there a converse, right? We know they're not necessarily equal. We just showed. right? But maybe uh, maximal is at least square root the size of maximum or something. Or maybe within a constant, it's always at least 100, or logarithmic or whatever, right? Is there any relationship, bounding maximal relative to maximum? Okay, so uh, let's suppose for simplicity that my maximal and maximum matchings are disjoint. Okay, I just have two matchings, they're disjoint. If they have edges in common, I'll just take them out. All right. Uh, so what I've done here is I've just overlaid the two matchings. Okay, and then I erased the other edges because they made my eyes hurt. All right. Is there anything conspicuous about this graph? Yeah. They don't share. Well, red and blue don't share. Okay, that's by construction. That's true. That's true. Okay, that's one observation. Other observations? Yeah, each vertex connects to one edge or two edges, but the degrees are all really small, right? Because it can only get one edge from each matching. So the degrees in this graph are all at most two. Okay. Now, if you have a graph or the undirected graph where all the degrees are at most two, then you can have like what would be an example of something with degree at most two? A cycle. So it could be a cycle. That would be degree two. What would be another example? Degree at most two. How about a path, right? You just walk along. That's also degree one's at the endpoints in degree two. So actually, if you take any two matchings and overlay them on top of each other and throw out the ones they have in common, you'll get a disjoint collection of paths and cycles. So this looks like it's all tangled up, but it should just be some paths and some cycles, right? So it's kind of a simple object. So here would be an example of a cycle where I've kind of grayed out the other edges. Okay, so, oh no, this would be a path, right? So we start here. Maybe I can erase this and retrace it. So we start here and you follow along, red, blue, red, blue, red, blue, red, right? And a cycle might look more like this. You start anywhere you want and you'll go red, blue, red, blue. All right, so these paths and cycles are, of course, alternating between the two matchings. Okay. Good. So now what I want to do is I want to compare the number of edges in red compared to the number of edges in blue. Red refers to the maximum matching. Blue refers to the maximal matching. Okay. Now in a cycle, what would be in this square? How do they relate? They're always equal. They're always even number of edges and it's equal number red and blue. Okay. What about uh, paths? Okay. So first of all, I'm claiming that assuming red is maximum, the number of red edges on the path must be at least the number of blue edges. But why? So in this picture, there's strictly more. I think there's 1, 2, 3, 4 red edges and 3 blue edges. But how come it couldn't have been reversed? Why? Yeah, so okay, it has something to do with the definition of maximum. Okay. So uh, imagine things were reversed. Can I reverse things? It's gonna get confusing. Okay, so hmm, okay, here's what I'll do. So imagine those two edges weren't there. So here, actually, blue is outnumbering red. Okay. So if it was not this case and you had more blue than red, then how can I find a contradiction with red being maximum? So this goes blue, red, blue, red, blue. I claim if this showed up, then red wouldn't be the maximum. Okay, so in this case, I could swap out all of the blue with all of the red. So I can take the red matching, and I could have deleted these two edges and added the three blue edges, and it'll go up by one. Okay, so if red was actually losing to blue on a path, I can swap one set for the other along this path and make red bigger. But red is supposed to be biggest, so that shouldn't happen. Okay. So so red will always beat blue if red is truly maximum, because otherwise it's an opportunity to improve your solution. Okay. All right. Good. Now, what about the opposite direction? So red will always be greater than or equal to blue if red's maximum. Now, so blue may be smaller, but I want to say, oh, blue is at least something times red, or something related to red. So I guess in the worst case, you have paths that start and end with red, and in between is it's going blue, red, blue, red, blue, red, blue. So what's like the worst ratio you can get? Half. So I think the worst is just red, blue, red. So, oh, okay. Uh, you always get at least one half of the maximum, okay, along these alternating paths. Okay, so right, so that's the worst case. So, uh, so along any cycle, I know that they're always tied, and along any path, uh, it seems like I've arbitrarily switched red and blue. Okay, this isn't consistent. Just stick with the colors. Red is at least blue, which is at least half of red. Okay, we'll find out which letter was supposed to be there. Uh, okay, this will be B. This will be A. So if you put everything together and you just, you first take your red and your blue, you overlay them on top, break them down into disjoint cycles and paths, and then just add up everything, then overall you're going to get your maximum is of course at least a maximal, but it's always at least half of the maximum. Okay, so for what it's worth, a maximal matching will always get you 50% of the optimum solution just by trying to add as many as possible till you get stuck. Okay. All right, good. Uh, so maybe you can throw this observation to the pro argument or NP hard, I don't know. But maximal matchings are better than nothing. They do get you at least half the score. Okay? The question is, can we push it to optimum? Okay. All right. So good. All right. So we're going to try to take an approach inspired by flow and yeah. Sure. So since A is maximal, uh, if you have a red edge, then, if red is taking this edge and blue didn't take that edge, then it must have some other edge incident to it on either side, right? Otherwise, it would just take this for free. So I guess if you had an edge just floating out there by itself, both red and blue will always take it. So that'll be okay. Yeah. Okay. So our goal is to see if we can drive this 1/2 approximation down to exact. And we'll see how far we can get by, something inspired by Ford Fulkerson and, what we would have done for bipartite matching. Okay. All right. So, good. This we know. Sorry, this is just all stuff we just did. Right. So, again, one of the points we made is that if in one of these paths, alternating paths, you actually had less red edges than blue, you could have made red bigger by exchanging, right? Uh, but B is already maximum. Yep. So that actually suggests an algorithm that's not so different than what we've done many times. So suppose we red here signifies edges in my matching, okay, and black are other edges that I haven't taken. So I'm building up a matching, incrementally over time. And these two endpoints, they're not attached to any edge right now. I haven't taken any edge, so they're free, right? So if I have a path like this in the graph and I find one, then what can we do? We can exchange, right? So we can remove these two edges from our matching, add these alternating edges, things have gotten better by one, right? So this would be called an augmenting path, right? And so that suggests an algorithm, right? Which is I'll start at some vertex that's unmatched and start trying to walk around unmatched edge, matched edge, unmatched edge, matched edge, and so forth until I find another unmatched vertex. So I have one of these augmenting paths, and then I'll exchange and increase my solution by one. If you think about it, that's actually what our Ford Fulkerson was doing on a bipartite graph. Originally, all the edges were directed forward, but every time I took an edge, it got directed backwards. So you were going back and forth, back and forth. Yeah. Yeah. A free vertex is a vertex that's not matched. So you have a matching right now, right? But there's some vertices that aren't incident to any edge in your matching. Those are what I'm calling free. Yeah. They might have edges that are in the graph, but you haven't used that vertex yet, so to speak, with your matching. Yeah. Free as in like freedom, as opposed to free beer. Or maybe both. I don't know actually. Okay. Um, okay, so right. So you have something like this, and you exchange it, you make some improvement. Okay, so now what happens if there are no augmenting paths? So let's say that you've come up with an algorithm that can keep looking for augmenting paths. Maybe you do BFS, DFS or something. We'll go to that in a moment. But and somehow you conclude there's no more augmenting paths. Then what? So somehow you've come to a conclusion that there's no augmenting paths left in the graph. Okay, to lead you on a bit, I claim that you must have an optimum solution, but how can I demonstrate or how can I argue this? I claim that if you have a matching and there's just no augmenting paths out there, then you have an optimum solution. There might be free vertices. So there might be vertices you're not able to find one of these paths that connect one to another with alternating edges. Yeah, certainly if you've covered all the vertices, you must be done. So the interesting case is when you haven't. Yeah. Uh, so you'll definitely have a maximal. Okay. So you take your matching, you remove it, and then you try to find more matchings on a residual graph. But that might just give you a second matching, but they're going to be incompatible with your matching. There's going to be lots of conflicts. That won't quite help. In fact, I'm trying to argue that if you reach a point where there's no augmenting path, you're actually done. And the only question is why. Yeah. No, there could be many unmatched vertices. You're just not able to get there along these black-red paths. There's no augmenting path. There may be paths and, there may be several unmatched vertices. If you only have one unmatched vertex, you're definitely done. So it goes back to this thing about the disjoint paths and cycles. So I can take my matching and compare it to the true optimum matching. Okay? So so right now I'm B. Uh, yeah, the A's and B's. A's and B's are just arbitrary. So here B appears to be some maximal matching, and A is the maximum again. So it got switched back. Okay, but the point is your solution B in blue. You have the guarantee that there's no augmenting paths. Okay, so when I compare to opt, I know that I'm tying already on all the cycles. If I take my matching, the opt matching, throw them on top of each other, it breaks down into A matchings edges we both took, and then disjoint cycles and these alternating paths, right? So cycles we're already tying opt, and on these paths, okay, if red is opt and blue is me, if I had a path that was like red, blue, red, then that would give me an augmenting path, right? But there are no augmenting paths. So in all of these paths, we're actually tied with red. Okay. So if there are no augmenting paths left, you're already tying on all the disjoint cycles, but you're also tying on all the paths, the alternating paths. You add that all up, and now you're equal. Okay. So if there's no augmenting paths, then actually that's a proof that you're done and you have the right solution. That may mean there's several free vertices out there that are unmatched, but there's just no way to get them involved in a way that improves your solution. Okay. Good. Making good progress. Yeah. Yes. Okay. So I think maybe if we go here, oh, well, here there's an odd number of edges. Uh, okay. So here we actually have two unmatched edges. We have two unmatched vertices. Oh, but there is an augmenting path. Okay. So here you could actually augment. So this would be an alternating path like this, and you can improve your solution. So this is not an example that you're looking for. Um, Gosh. Uh, okay. Maybe it's a little bit hard for me to come up with a whole graph and under time constraints. Maybe if we have time, I'll come back to it. Okay. All right. That's a good question. I should have been prepared for that. Um, uh, oh, I guess, yeah, if I add more edges like this, uh, you won't be able to match these vertices. You have lots of unmatched. I don't think on this graph you can do better than two. So you could take this one and this one, but then you can't take any of these in blue. And or you can try to take like, one of these, but then you can't take any of these and one of those. I don't think you can do better than two on this. Um, but you have lots of unmatched vertices. Okay. And so these are connected. I mean, this free vertex is right very close to this free vertex, but I can only go there from blue, blue, right? And that's not an alternating path. Augmenting paths need to go blue, red, blue, or something like this. So yeah, this would be then an example of, yeah. Okay, good. Wasn't so hard. All right, good. Where were we? Okay, so this is at least giving us some kind of path towards an algorithm because at least we have some criterion to decide we have a good solution, right? Like, yeah, you want to be able to at least recognize you have a good solution. So this algorithm in principle should be correct. I'll start with an empty matching, and then I'll repeatedly look for an augmenting path. I'll start at a free vertex and start walking around. If I find an augmenting path, then I can switch. I can do this augmentation along it and improve my solution. And if I conclude there are no augmenting paths, then I'm done. Right? So, good. So the next question is, how do we find an augmenting path? Right? So, for as a warm up, how would I find an augmenting path in the bipartite case? Suppose there's only one free vertex on the left. So we start our search from here. So I'm looking for a path that goes blue, red, blue, red, blue, red, blue, red, blue until I get to another free vertex. How would you do an augmenting path? Or alternatively, maybe you can direct me along an augmenting path. So I'll give you a quick chance to look and download this, and then I'll ask you which edge I should take. All right, you ready? Now are you ready? Okay. Oh, maybe. All right. So I'll start here. Should I take the upper edge or the lower edge to the right? Upper edge. Okay. And here you only have one choice in the opposite direction. Go red. Okay. Should I take the middle edge or the bottom edge? Bottom. Okay. And here I only have one chance to go from right to left. Now should I take the middle edge or the bottom edge? Okay. So that would be our augmenting path, right? Now, if we had more than 6 nodes on each side and it was a bigger graph, how would I automate this search? How would you make this algorithmic? Okay, running DFS. Now, maybe one thing we should be careful about is if you just ran DFS, right? DFS would not pay attention to the color, so DFS could go like that. Okay, that's how I'm asking. How are you going to do a DFS that takes care of all the complicated details? So there's an easier solution. Yeah. Yeah, so how, well, give me there's a nice clean way to make this auxiliary graph and I can just run DFS on it. Suppose you're just going to add directions to the edges. It's an undirected graph right now, right? How can I direct the edges to guarantee we go blue, red, blue, red, blue, red, blue, red? We're implicitly doing, yeah. Yeah. So we'll have the unmatched edges go from left to right. The matched edges go from right to left. And if I even want to automate like the starting point, I'll add edges to all the free vertices. Actually, there probably shouldn't be edges to anything that's already matched, but okay, so maybe I would actually want to erase this. But if there's more than one free vertex on each side, there would be more purple arrows. Okay. This is what Ford Fulkerson is doing, right? We had a super source and a super sink. Originally, all the edges were directed from left to right, but if I sent one unit of flow from left to right, then you add the reverse edge back in the residual graph. So this is actually what was going on, is you were always reversing the edges that you took in your matching. Good, good. So this is just Ford Fulkerson. Okay. What about general graphs? Right? Like here's a free vertex or something, right? Or here's a free vertex. What would you do in general graphs? So what's tricky about general graphs compared to before? Yeah, we don't have this left to right, right? So this direction trick doesn't work, right? It's not obvious how to do what we just did. Okay. And so here's something that can happen. Okay, maybe you come up with a very clever DFS that's at least smart enough to alternate between blue and red. Okay. So you go like this, blue, red, blue, red, blue. Okay, something very weird just happened, right? We got an odd cycle. Okay. So I always think of like the Pokemon song appearing, but you get this odd cycle where you actually went blue, red, blue. And maybe DFS would start going in the wrong direction where now it starts taking red and it starts going backwards, right? And you might end up where you started and be like, oh, I went from free vertex to free vertex, except it's the same vertex. Okay. So in a general matching, you can get these odd cycles. Blue, red, blue, blue, red, blue, red, blue, things like this. Okay. And that's really throwing a wrench into our augmenting path strategy. Okay. So, good. So in general, we're getting fooled by these odd alternating cycles. Okay. They're also called blossoms that we'll break down to some. Now, odd cycles like this can't happen in a bipartite graph. Right? So this is just something that wouldn't normally happen. Now, this odd cycle can be deceiving, right? Because, for example, there are augmenting paths in this graph. you can go like this, right? And then you enter this vertex, and if you can see it, you can go this way. Blue, red, blue, red, blue, red, blue, red, blue, red, and then out this way. Blue, red, blue, red, right? There are augmenting paths, right? So just because you found this odd cycle, remember some kind of search algorithm, you're just walking along, you can't anticipate, which turn it's supposed to take and stuff, right? And you're just walking along this way, and it gets stuck, and this can be very discouraging. And in fact, if it goes the wrong way, then it might not find certain things. So if you're trying to look for this augmenting path, and you went along this cycle in the opposite direction, right? Then you'll get blue here, and you won't be able to leave like you want to. Okay, so this is a bit of an issue. So this is what we want to try to figure out. Okay, so I don't know. Some creative people have come up with a terminology for this kind of thing. Okay, so in general, you start at a free vertex, then you have some path, and the last edge of the path will be a matched edge. Okay, because the odd cycle will kind of meet at two unmatched edges. That vertex where it meets is called the base. The path up to is like the stem of a flower, and then this odd cycle is called the blossom. Okay, so yeah, back when algorithmic design was more romantic. Okay, now we're just clubbed in the head by neural networks. There's no romance left. Okay, um, good, good. All right, so okay, you run your algorithm. It's alternating blue, red, blue, red, blue, red. Okay, it finds an odd cycle. What do you do? What do you do? No, we're going to do something more clever. Any ideas? This will be one of the more clever moments in the history of computer science. So what we're going to do is we're going to take, uh, yeah, let's see here. Should be set up. Okay, so we're going to take this and we're going to shrink it. Okay, so we're going to take this and we're going to shrink it to like a vertex. Okay, so we're going to replace that whole blossom with an auxiliary vertex and reattach this like this. Okay, when we find a blossom, we're going to shrink it. And then we're going to work in this auxiliary graph where that blossom was just replaced by a vertex. Okay. Okay. So, right. So it might look more like something like this. This will be the new graph that's left. So that whole auxiliary graph, the blossom is now treated as a single vertex, and any edge that was incident to something along this cycle is now just attached to the auxiliary vertex. Maybe. Well, let's see. Okay. So so then what you're going to do is you have this graph. It's a little bit smaller now because you shrunk a vertex. And now you look for another augmenting path. And let's say you find one in this augmenting path. Right? So this is just a vertex I can just kind of jump through. Right? So red and then blue on the other side. But of course, we need an augmenting path in the original graph. Right? This is not directly useful. So let's say I expand it out. Right? I expand back out the blossom. So that means the augmenting path is sort of getting split, right? Where it entered the blossom and where it left. But I want to try to recover an augmenting path overall. So if we zoom in on where this thing is leaving, it's leaving on a blue edge, right? And it's at some juncture in the cycle that has to go red and blue, right? So one of these two sides is red, in this case, the lower one. So you could go through the cycle like this, and you'll get an augmenting path overall. Okay, so when you find a situation, you can actually reconnect things through the blossom. So the blossom will actually let you go in either direction that's convenient for your departure. Okay. So if you find an augmenting path in the contracted graph, you can recover it. So here's another example of an augmenting path in the contracted graph. And when we uncontract it, this time you want to take the upper ridge, okay, to reconnect the two parts. Okay, so you can find augmenting paths in the contracted graph, expand back out. Okay, so that's the idea. When we find a blossom, this thing that's really painful, this thing that breaks our mind, we just shrink it. Okay, and we can actually look for augmenting paths in the shrunken graph and recover augmenting paths in the original one. And you can do this iteratively. You shrink, you find another blossom, you shrink again, you shrink again. Okay, so in the interest of time, I won't do it too slowly, but you want to prove two things. One is that, one we just did, is that if you contract the blossom and you find an augmenting path in the graph that's contracted, you'll get an augmenting path in the original graph. Okay, so it might be a little more clumsy to write out what we did in English, but I think the picture made it pretty clear. Okay, and vice versa, you want to make sure that if you have an augmenting path in the original graph, when you shrink the blossom, you still have an augmenting path. Okay. Now, this one would require a little bit more care normally because there's some weird things that can happen. So for example, let's say this is our blossom and you're looking at this augmenting path here. If you shrink this will no longer be an augmenting path because it's kind of going in on blue and leaving on blue. Okay. So although in the shrunken graph, this augmenting path got destroyed, you'll still get this augmenting path over here in this case. Okay, so good. All right, we're almost done. So that's the whole algorithm. Okay, it is an augmenting path algorithm, but the key idea is you find a blossom, you can shrink it. Okay, so you just find one, you shrink it. All right, so the running time. So each time you do like a breadth first search or depth first search, and then you find a blossom. So that takes linear time. Each time you find a blossom, number of vertices goes down. So you only need to do n of these. And every time you find an augmenting path, you add one to your matching. There can only be n edges in your matching. So you get mn squared. Okay. So this one can actually be done in polynomial time. Now, besides this algorithm being clearly very beautiful and very clever, there's good historical reason why I wanted to present it, especially at the end. So this paper is in 1963. Okay, so that's a really long time ago, even by my standards, and you probably think I'm really old. Okay, so for example, this is 9 years before that Richard Karp paper about all the reductions between NP-hard problems, right? So we haven't even clarified P versus NP yet, and in fact, it's 10 years before the C programming language, right? So you don't even have malloc at the point of this paper, right? And so at this point in time, it was not clear that we should even care about polynomial time algorithms. In fact, some people had already claimed that Ford Fulkerson just doing that willy-nilly will already give you an algorithm for matchings. And then admins were like, oh, there's these blossoms. You can't just do augmenting paths like that, right? And so here it says, look, see this, okay, the extensive combinatorial linear theory on linear programming by Ford Fulkerson and also Hoffman. So section 2, see, maximum matching non-bitartite graphs is present unusual, unimodular type. Okay, we didn't talk about that. So section 2 is a philosophical digression on the meaning of efficient algorithm, right? So that's one thing that's spectacular. This is one of the first really non-trivial polynomial time algorithms. Is okay, this is much more interesting than exponential. So here, look at this sentence, right? there is an obvious finite algorithm, like trying everything, but that algorithm increases in difficulty exponentially with the size of the graph. It is by no means obvious whether or not there exists an algorithm whose difficulty increases only algebraically with the size of the graph. Algebraically is their word for polynomial, right? So this paper is still making this argument, and it's just, yeah. So this is a significant, very significant paper, right? When the measure of problem size is reasonable and when the size of the assumed value is arbitrarily large, an asymptotic estimate of the running time is theoretically important, right? So he's looking for running times and he's trying to identify polynomial running times as significantly more interesting than exponential time where you just try everything, which is what people were actually suggesting at the time, right? So for practical purposes, the difference between algebraic and exponential order is often more crucial than the difference between finite and non-finite. Okay? And then, so that this is just an amazing paper, and he even lays out, a massive question. How good is a particular algorithm for linear programming, the simplex method, right? So we don't figure out a polynomial time algorithm for linear programming for another 20 years. Okay? And simplex is still actually not polynomial time, but often preferred in practice. So this is just a historically massive paper. Okay, so he says that the running time is n to the fourth because he's not counting edges. So r mn squared, he just says m is at most n squared. So right, and then he talks about a tree is grown by branching from a vertex. That's like BFS, DFS, but that terminology wasn't so common. Okay, so yeah, so this is a tremendous paper by Jack Edmonds, which to some extent sort of ushers in really the whole theme of this class, right? Focusing on polynomial running times, things like this. So, 1963 is maybe arguably a starting point for this era. There's some interest before, but this was maybe a really big argument. Okay, so that's it for all the real lectures in this class. And next time I'll just print out some questions on last year's final or something like this. Okay, all right, thanks guys.